Okay, so that's our discussion of the stability region of backward Euler. It's very different from the stability region of our previous type of schemes, right? And here we use this example to actually telling you a way to analyze the stability region of any ODE solver, really. For example, if you discretize using forward Euler, you can use the same analysis to write un plus 1 is equal to 1 plus lambda delta t times un, right? And you can compute the amplification factor the same way. Amp2, let's say forward Euler, is equal to, as opposed to this formula, I have 1 plus lambda delta t, right? And I can make another figure. Okay, I can serve the same way, but ABS of amp forward Euler, I would get something like this. And if I do shading interp to get the colors to be in the right order, and I also make the z limit to be 0 and 1, what I get is like a cone like this, right? As opposed to backward Euler, which is a huge region except a hole. The forward Euler is only stable like inside a hole. So if I do the same thing as I did before, like z-axis, color bar, and view 2, what I get is this. So that is the stability region of forward Euler, as opposed to this guy, much bigger, backward Euler. Forward Euler, backward Euler, very different. All right. And in the future, if you encounter any other ODE integration scheme, you can figure out the stability region using that way. All right. So that's about backward Euler. But the now, given that we have the tool to design a scheme that is implicit, okay, that is, we are allowed to say we are computing our un as opposed to un plus 1 minus. Okay, so let me revise what I said. I'm approximating this time derivative du dt equal to fu, right? In previous method, we always in an implicit method, this du dt always have to involve un plus 1, right? Because that's how, when we convert the time derivative into an ODE solver, is the solution at n plus 1 that we move to the left hand side to solve for the next step. All right. Now we are allowed to discretize this scheme, the du dt, using only the current time and the past time. All right. Can you now go ahead and design schemes that are more accurate than backward Euler, but are still implicit? So here I give you a task. Can you design something more accurate than backward Euler, but is still implicit? And you can ask me to do any stability analysis for you once you design such a scheme. All right. So let's go, and with the group discussion again, whoever who figures out one scheme that you want me to test the stability on, just call me. All right.